Okay, now we'll look at um, double integrals in polar coordinates. Okay, just to review, we know that x squared plus y squared is r squared. We know x is r cosine theta, and y is r sine theta. And if you remember, if we just had any circle, x squared plus y squared equals k squared, where k is a constant, then we can change the polar coordinate. We can just say that that circle with radius k is r, or if we say, let's just say inside the circle. So we want all this. Then we want everything between, we want the radius to be between 0 and k, out inside and the boundary. And theta can go from 0 to 2 pi. We want it to go around the whole circle. So we'll get the whole circle as we go from 0 to 2 pi, and the r part gives us the inside of the circle. So to express something like, let's take this donut shape, and we want between the two circles, the equation of this one is x squared plus y squared equals 9. And the equation of the inside circle is x squared plus y squared equal 1. Well, if we just want above the x-axis, this part we can say r is between 1 and 3, because the radius of the larger one is 3 and the radius of the smaller one is 1. And we can say theta is between pi and 0, and that gives us this whole first and second quadrant. So that would be the equations in polar coordinates for that half of a donut. So sometimes it's easier to get to polar coordinates, to do the integrals. So if I have some region I'm integrating a surface over, then I can say in polar coordinates that's going to be theta is from alpha to beta, and r goes from A to B. And these A's and B's could be functions of theta. Then to change it, we would use this formula. Okay, and notice there's an extra r here, and I'll explain where that comes from. But again, you're going to integrate with respect to r, and then you integrate with respect to theta. And the region we're talking about, this r right there, is where the radius is between A and B, and theta is between alpha and beta. And also, if you subtract beta and alpha, it's less than or equal to 2 pi. So we're not going around the circle. We're not going over and over around the circle. Okay, let me, instead of proving it, let me explain where they get that extra r. First off, we talk about an area of a sector. That's like a piece of pie. Is 1/2 r squared theta. So let me draw a sector here. This is called a sector, a piece of a circle. And we'll call this delta theta. And this is going to be delta r, the change in the radius. And we'll say this is r1, and this is radius 2. And in between the average, will be r1 plus r2 divided by 2. So that's going to be the average of the two radiuses. Well, this area of the sector in this case is going to be 1/2. I want this piece right here. R1 squared minus R2 squared delta theta, and that factors and this is the average radius. Let's call it R bar. This is the change in R delta theta. So this translates to the R, this translates to the dr, and this is the d theta. So there's where that extra R comes in when we integrate. We're going to say that this is delta A, the change in the area. So that translates to dA. Okay, let's do an example. I want the volume. It's going to be a volume if the f function is positive. So I want the volume of the solid bounded by z equal 4 minus x squared minus y squared in the first octant. So let's see. I know x squared plus y squared is r squared, so we have to change z equal 4 minus, we can factor out the negative, and that changes to 4 minus r squared. So there's our function. If we're in the first quadrant, z is positive, first octant, so that says that r has to be between 0 and 2. And theta has to be between pi over 2 and 0, because if we draw it, we have this parabola and that's what it looks like. So you can see theta is from 0 to pi over 2 in red, that's theta, and r is from 0 to 2, because the base is that circle. Right here, this circle is x squared plus y squared equal 4 in the xy plane. You let z be 0. Okay, so that gives us our boundaries when we integrate. First, let's integrate 0 to 2. That's our r. Then we have the function. We have r dr. Then we do the theta from 0 to pi over 2, d theta. So that's what we integrate for this problem here. I'm not going to do the integration because it's not very difficult. I'm just going to set it up. Okay, the same problem in rectangular coordinates, that means x and y. If we look, the base of the region looks like this with radius 2. So let's go from here to here. This is y equals square root of 4 minus x squared. So we integrate y first. Doesn't matter in this case. And then that's going to be from 0 to 2. And that should give us the same answer in polar, because that polar is probably more or easier. Okay, here's another example. I want the region inside and outside are equal 1. Okay, when we're in two-dimensional and we just want an area, because this is going to be area and it's not a volume, then we let our function equal 1. So it's just a flat surface. It's a flat plane since z equal 1 parallel to the xy plane. So it doesn't matter where it is, it's still going to have the same area, whether it's in the xy plane or whether it's 1 unit above it. Doesn't matter. Okay, so let's draw a picture of this. There's the circle unit 1. Well, it's not very good, but. And then r equal 2 sine theta, so it's 0, it's 0. At pi over 2, it's 2. So the circle looks like this. And I want inside that and outside the other one. So I have to find their points of intersection. So 2 sine theta equals 1. Sine theta is half at pi over 6 and 5 pi over 6. Okay, so let's go this way. That's our radius, difference in our radius. So first we do dr. So r is going to start at 1 and go to 2 sine theta. And theta is going to go from pi over 6 to 5 pi over 6. And my function is 1 times r dr d theta. So anytime you want to find the area that's two-dimensional, then you just let your function equal 1. Okay, I'll go ahead and integrate this, even though it's not too hard. First, it'll be r squared over 2 from 1 to sine theta. Plugging it in, I'm going to get 4 sine squared theta over 2 minus a half. So that's 2 sine squared theta minus a half. Then I'm going to integrate that from pi over 6 to 5 pi over 6. But to do the first one, I'm going to use the half angle formula. And that is sine squared is 1 minus cosine 2 theta over 2 minus a half d theta. The 2's cancel. So this is going to be 1 minus a half is a half theta minus, and the integral of cosine is sine. And we go from 5 pi over 6 to pi over 6. Okay, so that's going to be 5 pi over 12 minus 1/2 sine 5 pi over 3 minus pi over 12 minus sine pi over 3 1/2. Okay, that's going to be pi over 3. Okay, and sine 5 pi over 3. Let's see. Let me draw a picture. It's over here. So that's pi over 3 is negative square root of 2 over 2. So that's going to be square root of 3 over 2. Let's see if I got plus times a half. Okay, I have to keep saying what I did. Okay, plus a half sine pi over 3. And sine of pi over 3 is square root of 3 over 2. So this is going to be pi over 3 plus square root of 3 over 2. Okay, so that's all you need to integrate using polar coordinates.